Assalamualaikum and hello everyone. In this video, I would like to talk about shallow foundation. In civil engineering, when we talk about foundation, it means that it is a part of a structure that transmits load from the superstructure to substructure, or in other words, soil. So if we refer to this figure, let's say this is the structure, or in other words, we call it as superstructure. And below the ground surface here, we could see a component of the structure. These are known as foundations. So the foundation here, we have footing and we have pile. So the footing and the pile, their functions are to transmit load from the superstructure to the soil. Okay, when we talk about shallow foundation, so we enlarge this footing. Right? So let's say this is the ground surface, and this is the footing with the dimension or the width B, and the depth of footing is dF. So based on these dimensions, width and depth of footing, we can categorize the foundation into two. One is known as shallow foundation and another one is deep foundation. How to differentiate or how to define which one is shallow foundation, which one is deep foundation? Okay. So based on the depth of footing and the width of footing, we take the ratio. When the ratio of dF over B less than or equals to about 3 to 4, then the foundation is categorized as shallow foundation. However, when dF over B greater than 4, then the foundation is categorized as deep foundation. Shallow foundation can be categorized into 4 generally. The first category is known as isolated footing. Some people call it packed footing, some call it spread footing. Generally, one footing supports one column. That is known as isolated footing. The second category here is combined footing. Normally, one footing supports two columns. The reason for having this combining footing, among other things, is because the footing are too close to each other. That's why those footings are combined. That's what we call it as combined footing. The third category is strip footing, meaning the footing is very long, or in other words, the ratio of B over L, B is the width of the footing and this is the length. So the ratio of B over L is very, very small. Okay. Some people categorize strip footing when the ratio of L over B about 20 or so. Whenever the ratio of length over width about 20 or so, it's considered as strip footing. Normally, it's constructed to support load-bearing wall, or maybe to support retaining wall, very long retaining wall. The fourth type here is known as rough foundation. It's a big foundation to support several or many columns. So this type of foundation normally is expensive, but can be constructed rapidly because they can minimize the number or the time to construct the formwork to construct this type of footing. In designing shallow foundation, there are two aspects or two factors that we have to take into consideration. First, we have to make sure that the footing or the foundation will not cause shear failure to the soil supporting it. And number two, we have to make sure that the footing or the foundation will not undergo excessive settlement, because some structures, they cannot tolerate settlement. So in many cases, settlement govern the foundation design, right? Let's take a look at the mode of failure in shallow foundation. In this diagram, let's say this footing is placed in dense sand or well compacted soil. Okay. Then when load is applied gradually to this footing, meaning the load is increased with time, and then when we plot the load per area or the pressure against settlement, we could see the settlement will increase with the increase in load per area until a point whereby the load per area decrease but the settlement keep on increasing. So in this case, the mode of failure, we could see these are the failure surface. Right? When the pressure reach this value of Q sub U, or the ultimate bearing capacity, so the failure surface will extend to the ground surface, and then we could see the bulging, smooth bulging. In this case, it's considered or is known as general shear failure. Right? In general shear failure, we could see the peak of the pressure, right, whenever this failure takes place. In the second case here, the same footing but is placed in a relatively medium compacted soil, right? So when load is applied gradually, the footing will also settle with the increase in load per area. So until this point here, the failure surface will form up to the ground, up to the base level of this footing, and then the continuing application of load will cause the failure surface to extend upward, and the failure takes place whenever the value of Q sub U here is achieved. So in this case, we cannot see the peak of the load per area or the stress here, but in this case, Q sub U is defined at this point, and in this case, it is known as local shear failure. The third type of shallow foundation failure, the same footing placed in relatively loose sand or poorly compacted soil or not well compacted soil, right? When load is applied to the footing will settle, and if the load over area is plotted against settlement, so we could see the settlement increase with the increasing of the applied load. Right? So, and then there's a point whereby Q sub U is achieved, but unlike in the previous two cases, in this case, the failure surface is not extended to the ground surface, but this footing is punching the soil downward. This is what we call punching shear failure. So there are three categories or three types of shear failure in shallow foundation. The first one is general shear failure. Normally, it takes place in dense sand or well compacted soil. Second type is local shear failure. Takes place in medium dense sand or medium compacted soil. And the third type is punching shear failure. Takes place in loose or not well compacted soil. Before we can design a shallow foundation, let me talk about bearing capacity. What is meant by bearing capacity? bearing capacity is the maximum pressure that can be supported by a footing without causing shear failure to soil supporting the footing and will not cause excessive settlement. Right. What are factors that govern bearing capacity? Actually, there are three factors that we have to consider in determining bearing capacity of a footing. The first one is in terms of the soil which support the footing. So when we talk about the soil, there are certain parameters or characteristics that we have to take into consideration. First one is the unit weight of the soil, gamma. Number two here, in terms of soil, is the shear strength. When I say shear strength, I'm referring to the strength parameters of the soil, namely the cohesion C and the internal friction angle phi. The third factors related to soil, that is deformation characteristics. So when we talk about deformation characteristics, I'm referring to the three types of shear failure in shallow foundation: general shear failure, local shear failure, and punching shear failure. If you remember what I said about the mode of shear failure, those failures depend on the deformation characteristic of the soil, depending upon the condition, dense, well compacted, or loose, and so forth. Those are about the soil. Second factor that affect the value of bearing capacity of a footing is the footing itself. When we talk about the footing, we are referring to the size, whether it's big or small. The shape of the footing could be rectangular, could be circular, could be straight, and depth. How deep we place the footing in the soil. Right? And the third factor is groundwater table. Because groundwater table, the higher the groundwater table, it will affect the strength of the soil. So these are the factors that we have to consider when we design our shallow foundation, because they are related to the value of bearing capacity. Okay, let's talk about Terzaghi's theory on bearing capacity. So based on this diagram, let's consider a footing with the width of B, and the depth of footing here, the base, the location of the base relative to the ground surface is df, known as depth of footing, right? And then vertical load V is applied gradually. Okay? So in this diagram, okay, when load V is applied gradually, it will cause movement in the soil below the footing. Right? So based on model by Terzaghi, there are several wedges that we have to consider in this diagram. So these wedges are formed during the application of the load. Right? So once B is applied gradually, wedge number 1 is moving downward and will cause lateral movement to wedges number 2 and number 3. Okay. So based on this model, later on I'll show you the equation that can be used to estimate the ultimate bearing capacity. So there are several assumptions made by Terzaghi based on this diagram or based on this model. Okay. So this soil with the soil properties of unit weight gamma, C, the cohesion and friction angle phi. If you see here arrow pointing downward, that shows the overburden pressure from the ground surface to the base level of the footing, expressed as Q equal to gamma multiplied by dF. Okay. Right, the assumption made. First, soil is assumed behave as plastic material, when we talk about plastic material, it means once the soil deforms, it will not go back to its initial condition. Unlike elastic material, when once it deforms, it will go back to its initial condition. So in this case, it is assumed that the soil behaves as plastic material. Assumption number 2, shear above base of footing is neglected. So shear within this region are neglected. But at the same time, soil above the base of the footing exerts overburden pressure, as I mentioned previously, which equals to Q equal to gamma multiplied by dF. Assumption number 3, the application of V causes punching downward in wedge number 1, which causes lateral movement to wedge number 2 and number 3. And assumption number 4 here, movement of wedges number 2, lateral movement of wedges number 2 and number 3, lateral and upward, are being resisted by the shear stress along the failure surface up to the base level here. Here, up to the base level here. Because remember, assumption number 2, shear above base of footing is neglected. So there will be no shear here. No shear here. The movement are being resisted by shear along the failure surface as well as the overburden. Those are the assumptions made based on this model. So based on the model and assumption made, 3 equations are formulated depending upon the shape of the footing. First equation is for strip footing, meaning the ratio of the length to the width of the footing is very large. It's expressed as small q sub u, ultimate bearing capacity, equals to C n sub C plus Q n sub Q plus 0.5 gamma B n gamma. Okay, I'll explain what C and other items in the equation later. Okay, the second equation is for rectangular footing. Q sub u, small q sub u, equals to 1 plus 1/3 B over L multiplied by C and C plus Q and Q plus 1/2 multiplied by 1 minus 0.2 B over L gamma B and gamma. Whereas for circular footing, Q sub u equals to 1.3 C and C plus Q and Q plus 0.3 gamma B and gamma. So if we look at these 3 equations, there are 3 groups of items here: CNC, CNC, CNC. So these items, I call it as C terms. And then we have here Q and Q, Q and Q, Q and Q, I call it as Q term. And the last here, gamma B and gamma, gamma B and gamma, gamma B and gamma, I call it as gamma term. So let's take a look at the items in those equations. C is the cohesion of the soil, the unit kilonewton per meter square. So if the soil is uniform, we can take the value of C from the top or from the ground surface until below the base of the footing, C. So in reality, C should be taken from the soil below the base of the footing. Right? C should be taken from the soil below the base of the footing. Q is the effective stress at base of footing. Meaning, we have to calculate the stress or effective stress from the ground surface to the base of the footing. Generally, Q is equal to gamma multiplied by dF, the unit width of the soil multiplied by the depth of footing, expressed as kilonewton per meter square in terms of stress. Gamma here is unit weight of soil. So you have to be careful when we use gamma, because in Q here we have gamma. In gamma terms also we have the item gamma. So for the Q here, gamma, we take the gamma of the soil above the base of the footing. Whereas in the gamma term, we take the gamma below the base of the footing. Okay? So be careful with the gamma. B is the width of the footing in meters. L is length of footing also in meters. So N sub C, N sub Q, N sub gamma are bearing capacity factors. So you can refer to any geotechnical engineering textbook, or you refer to the yellow books, right? So go and look for tables for bearing capacity factors for Terzaghi's equations. So these equations are valid for general shear failure mode. Capacity. So this equation, that's what is called general equation. Only one equation to cater for different shapes of foundation. Unlike Terzaghi's equation, they have different equation for different shape of footing. So the ultimate bearing capacity based on Meyerhof Hansen's general equation, Q sub U is equal to C and C. Additional factors here, FCS, FCD, FCI, plus Q and Q. Here are the additional factors, FQS, FQD, FQI, plus 1/2 gamma B and gamma. Additional factors, F gamma S, F gamma D, F gamma I. Just like Terzaghi's equation, we have C term, Q term, gamma term. C and C, Q and Q, gamma B and gamma, similar to Terzaghi's equation. But we have to consider the additional factors. If you refer to the additional factors here, F's in the C term of the F's, the subscript start with C, FC, FC, FC. But the second subscript, S, D, I. Similarly, in the case of Q term, the F's here, the subscript start with Q, FQ, FQ, FQ. But the second subscript, S, D, I, similar to the C term, S, D, I, S, D, I, here S, D, I, S, D, I. The gamma term here, 1/2 gamma B and gamma, F gamma S, F gamma D, F gamma I. The F's start with the subscript of gamma, 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 showing this in the gamma term. And then the second subscript, similar to C term and Q term, S, D, I. Okay, let's take a look at the definition of the items in the equation. C, just like in the Terzaghi's equation, represent cohesions of the soil. Gamma is the unit weight of the soil. And Q here is the overburden pressure at the base of the footing. Similar in the case of Terzaghi, generally equals to unit weight of the soil multiplied by the depth of the footing. NC, NQ, and gamma, these are the bearing capacity factors. If you refer to any geotechnical engineering books, you refer to the table for these bearing capacity factors for Meyerhof Hansen's equation. Don't get confused. Don't interchange. Terzaghi's equation has their own table. Meyerhof Hansen's equation has its own table. FCS, FQS, F gamma S. So the last subscript, SSS, for C term, for Q term, and for gamma term, the subscript S represents shape factors. In order to obtain shape factors, there are certain equations that we need to use. Right? FCD, FQD, F gamma D. The second subscript, D, it shows depth factors for C term, Q term, or gamma term. Depth factors. These factors also, we have to refer certain equation to calculate the FCD, FQD, and F gamma D. Lastly, here is the inclination factors. FCI, FQI, F gamma I. The I here represent inclination of the load. So the inclination of the load is expressed in terms of degrees, but the measurement must be made with respect to vertical axis. Let's see. This is the footing. So under certain circumstances, maybe the load that to be carried by the footing is inclined. So let's say this is the vertical axis, and let's say this is the load, sorry. So let's say this is the load. Let's say load Q. So the inclination is measured with respect to vertical axis. This is the beta. So by comparing those equations, Terzaghi's equation and Meyerhof-Hansen's equation, Terzaghi's equations are more specific to certain shape of footing, and then the loads are considered as vertical. Whereas in Meyerhof-Hansen's equation, it can be used in any shapes of foundation, but the load not necessarily vertical. Inclined load also can be used in this equation. But in Terzaghi, we cannot estimate the bearing capacity when it involves inclined load. So in the next videos, I will explain, or I'll show you example how to use Terzaghi's equation and how to use Meyerhof-Hansen's equation to estimate the ultimate bearing capacity.